Hi, and welcome back to the data science course. We're still in part one, which is machine learning and data analytics. In this lecture series, we'll learn about another type of supervised learning algorithms called classification. So we discussed selecting the right algorithm for your problem and data as part of the data science process lecture. So let's have a quick look at that again. If you remember, based on the predictions that you have to make, whether they are numeric, continuous, or whether they are categorical or discrete values, and whether they are labeled or unlabeled. So classification is used for labeled data, and it predicts output categories or classes which are discrete values like 0, 1, 2, 3. And it has its own set of models or algorithms, and they are split into linear and nonlinear problem types. And then again, the sample size will determine whether we can use certain models or things like neural networks. Okay, so let's understand the basics of classification algorithms. They're used for predicting a class or category for an observation based on the training from the sample data set. So just like regression algorithms, you get the data, you train the model on it, test it, and then you predict the y values. The difference being that in regression algorithms, you were predicting continuous numeric values like uh, 13.45, 129.678, and so forth. You can go into any range there. But in classification, you're predicting categories or classes which are discrete values, so like 0, 1, or 2. So simple example is true or false, which is 0 and 1, or male and female. So these are simple discrete classes. So the classification algorithms predict the class for the output variable y, which is also your dependent variable, and it uses the independent variables x as the input, which is also called as the feature set. The algorithm itself is called as a classifier or model. So this is the difference in terminology. In regression, we call them as estimators, and here they are called as classifiers. So just take note of that. Similarly, it has a training set and a test set. So your training set is used for training the model, and test set is used for testing the results of the model. Now, being supervised learning algorithms, the data is labeled. So the model, the data it gets, the dependent variables y are already available for each row of independent variables x. So it needs to know that what combination of x variables gives what y. So it has to learn from that. And that's because the training data is already categorized correctly. I mean, that's what we expect from the data. I mean, and then the model will learn from that. And then the test set will contain only the independent x variables, which will then be used by the trained model to predict the y values. And these y values can then be compared with the actual y to measure the accuracy of the model. The objective is to build a classifier that can assign any new observations or new data to the correct class or category, which is exactly the same for all models. You want to train the model on past historic data. Then you want to pass it new data to see what the output predicted values would be, and you want them to be as accurate as possible to the real world values. The basic concept used by most classification models is the term called similarity. Effectively, it uses a similarity measure like Euclidean distance. Now, Euclidean distance is something you are all aware of. It's the straight line distance between 2 points A and B, and something you do quite often. You know the distance between your home to work, to your school, or to the grocery store, or your distance from one city to another. They are all Euclidean distances. Another term which is used is cosine of the angle. Now, the cosine is effectively the angle between the surface and the object. So, if you imagine your two dimensions here, and if you had a line which has a slope, that slope is effectively the angle of that line to the base. And what the cosine of the angle similarity measure does is it ignores the magnitude of the line and instead looks for similarity based on the angle. So if two lines are very similar in terms of their angle to the base or the x-axis, there is some amount of similarity in them. So what the model does is basically it takes the feature set of independent variables, converts them into a vector of points, which effectively becomes a line, and then it looks for the distance between these lines to assign them to the class or category. So remember, this is labeled data, so it's already learned from the training data what a combination of x input variables, which is the vector of points, uh, represent in terms of the output variable y or the class. So it knows that what kind of a line or a vector of points belong to which class or category. So when it gets some new observations, which is new rows of data containing x independent variables, it converts each one of them into an independent line and then looks for the distance or the angle of that line from the classes or the categories, and then accordingly allocates them to that based on the similarity measure, be it distance or the cosine of the angle. Now, in these lecture series, we'll be covering only distance-based measures. Okay, so let's look at a visual example. Right, so you've got this sample data of points. They're plotted on this two-dimensional chart. You've got the x-axis and the y-axis. So effectively, each point has some x value and a y value. Now, all of these points are currently scattered, but there's a good possibility that some of them are similar and can be categorized into one group, and another set of points are similar in another way, and they can be categorized into another group or class. So what the classifier does is it looks for that similarity based on the distance. So it can start with one particular point from the data set, or use some seed value, and then tries and assigns the points based on their distance from this initial seed value, and then creates a class or a category, and then it does that for another class or category. So effectively, the result will be two classes A and B, with a set of points assigned to class A, another set of points to class B. Now, what happens is that if you get a new observation, a new data point, the classifier will then see the distance of that point from the points of the two classes. And in this case, you can see that the red point is closer to the green points compared to the blue points. It's a pretty obvious distance measure. So it will assign it to class B. However, if the red point was somewhere here, then it would have become difficult because it would have been closer to some points in A and some points in B. That's when the models use some smart techniques to find the best fit class. And now, if you extend this concept of the point from being just one x variable to multiple x variables, you can represent that as a vector, and that vector will have its own magnitude and direction, and then you can apply the algorithms to find the distance between the vectors. And there are different mathematical techniques available to calculate this distance, which we'll cover as part of the different classification algorithms. Okay, now classification is generally of two types. One is binary and the other is multi-class. So binary is when you have only two classes. Simple example is 0 or 1, or true and false, or male and female. So your entire data set, the output values are categorized into two classes. Extending that concept, now you can have more than two classes. So it's called multi-class. In that case, you can have classes 0, 1, 2, 3, and it can go on. Remember, these are discrete values, not continuous values. So that's why you have 0, 1, 2, 3. And 0 again is used because, if you remember, in Python, all your indices are 0 based. And the same concept is used by your different machine learning algorithms. So multi-class categories could be for names of cities, it could be used for names of colors, it could be used for different types of diseases. So if you think about certain examples for which classification can be used, a very good example is assigning true and false to your output based on the input data. I mean, that's pretty common. You use that for many different fields. Uh, Another example is email spam. So, you can categorize the email as spam or not spam based on learnings from the prior spam data. So you look for keywords, you look for the senders, you look for the subjects. These are the input X variables. And based on that, you can decide whether the email is spam or not spam. Another good example is detecting the presence or absence of a disease by using prior disease symptom data. So, if you think about it, there are a lot of symptoms which could indicate different diseases. If we have enough data from a lot of different patients, there is a possibility that you can classify into the right disease based on the symptoms. And we briefly discussed a disease symptom example for cholesterol in the probability chapter for conditional probability. So what you'll realize is that in the real world, there are a lot of examples in different industries which can be modeled using classification algorithms. So some of the more popular classifiers are logistic regression, k nearest neighbors, support vector machines, naive biased, and then of course decision trees can be used for classification and neural networks. But we won't be covering neural networks as part one of this course. It will be in part two for the advanced machine learning techniques, and we've already mentioned why that is. So classifiers use their own error metrics like confusion matrix, ROC curve, which is receiver operator characteristics. So we'll explain what these metrics are and how they are calculated. Effectively, what they do is they look for whether the predicted class or category for the output variable y is correct or not. So whether it's a true and false, and then it performs different calculations. So we'll show you how to do that. Uh, Now, this is something which we've mentioned in the data science process and for regression, that as the machine learning models, in this case classifiers, work with numbers, and the data can be numeric, which is integers or reals, or ordinals, which is your true false type data, or categorical, which is just text data like cities, group types, or just textual information regarding the data, and you need to transform it into numbers. And we've already shown you how to do that in the data wrangling chapter. So you need to encode the data, you need to bin the continuous data, and clean the data, all those steps we've shown. And since these classifiers are distance based, so the measure they use for similarities, generally Euclidean distance or some other distance measure, you will need to do standardization. And again, we've explained why we need to do standardization to ensure that when you have variables with the different ranges, you don't want data with a higher range to be given a higher weight, and instead you want to compare them on a equivalent scale. So you need to center the data around the mean with mean 0 and variance 1, which is your normalization, or you can have a mean with the variance of the same order. So effectively, you want to reduce the variance in the data. This is done to prevent the outliers from getting a higher weight in the model, which could result in bad predictions for the new data. And you only want to standardize the training data, not the test data, because if you standardize the test data, it'll have its own mean and variance. So if you're trying to compare the results for the predictions for the test data with the actual data, you will have a completely different distribution. So it's not a good comparison. We've explained all this before in the data science process and the data wrangling steps. So you can just go back and learn that again if you've forgotten it, or you want to refresh it. Now let's look at the error metrics. So the most common and widely used error metric for classification is the confusion matrix. And what it does is it allows you to evaluate the accuracy of the classifier. And how does it do that is it tells you how many of your predicted values, the y values, are in the correct class or category. And the way it does that is by building a matrix of your correctly and incorrectly predicted values against the actuals. So what you have is a n by n matrix. So if we consider a binary classifier, you'll get a 2 by 2 matrix, right? Because you only have two classes or two categories. You can represent them as true and false, or 1 or 0. And systemically, the model will again be numeric, so it will represent them as 1, 0. Each row represents the actual values of the data for the y output variable, and the columns represent the predicted values. So just remember, true and false means the two categories, 1 and 0, right? So if the actual value is true and the predicted value is true, so your y output has been correctly labeled or correctly classified. So in that case, it's a true positive. However, if the predicted value is false but the actual value is true, it's a false negative, right? So the model incorrectly predicted the true value, so it's a false negative. Similarly, if you take the false row, the actual value is false but the model predicted true, so it's a false positive. So you thought you'd correctly predicted it, but it's incorrect. And then finally you have true negatives. So the actual value is false and the predicted value is false, and it's called a true negative. So your true positive and true negative represent the correct predictions, and false positive and false negative represent the wrong prediction. So again, remember, you've got training data, you trained the model on it, the model learned what the y labels are based on the input x variables, and then you tested the model using the X test values, predicted the Y values, and now you're comparing those Y labels, the categories 1 or 0 in this case, against the actual test Y values, right? And that's when you measure which is right, which is wrong in terms of the predictions, and you get these cell values, which represent the total values for correct or incorrect predictions. Now, this false positive and false negative, they're also called as type 1 and type 2 errors. Both are useful. They can be important under different scenarios. So let's take two examples. One is disease detection, the other is fraud detection. So in the case of a fraud, let's say you have a company which is assessing the risk of lending to a fraudulent client. So let's take the two scenarios. So you know the client is a fraud, so the actual value is true, but the model is predicting a false. So what you have is a false negative or a type 2 error. Now in this case, there is a huge risk to the company because there's a possibility that the client who's borrowing will not return the money, and that will be a loss to the company. So the error of the model, which is the type 2 error, is critical in that case. Take the other scenario. Now the client is not a fraud, so the actual value is false, right? But the model predicted it as true, so it's a false positive or a type 1 error. So what's happened here is that you actually not lent to a good client. So the benefit is that the company would not suffer a loss because of the money not being returned. But the slight drawback is it's a lost revenue. But at least the loss impact has been reduced. So in this case, the type 1 error is useful, but the error's impact on the company is limited. Whereas in the case of the type 2 error, it was critical because you've lost a lot of money there. Similarly, take the example of disease detection. Let's say the person doesn't have the disease. So in that case, it's false. The actual value is false, but the model is predicting it's true. So it's FB or a type 1 error. Now, in this case, if it's a simple disease, like a severe cold or a stomach upset, maybe, even if you get treated for it, maybe the side effects or the impact on the patient would be limited, but you still don't want that. I mean, you don't want to give medicines for a disease which you don't have. However, if it was a severe disease and you got unnecessarily treated for it, you could have a fatal problem. So you don't want that. So the type 1 error is important. Now take the other scenario. So you have the disease, but the model is predicting false. So what's happened is you've got a critical disease. You should have been treated for it, but because of the model, you weren't treated, and that can be life-threatening. So you don't want that either. So the type 2 error or false negative is also critical. So it's not straightforward to say, one type of error is more important than the other. So you have to consider the problem and the data. So you can see that, in classification, you don't have one error measure like in regression. Mean squared error, R square, root mean squared error, but it's a combination of the predicted values in different ratios. Now, using these values, these four TP, TN, FP, FN, you can have some other metrics. They're useful. So let's look at some of them. One is the accuracy rate. So the accuracy rate is the correct predictions, TP plus TN divided by the total predictions, which makes sense. You want to know how many Y labels were accurately predicted, irrespective of the category or class, be it true, false, or a 1 or a 0. So TP and TN versus the total predictions. So, similarly, you have the error rate, which is 1 minus the accuracy rate, because this is a ratio, right? So a percentage of the accurate values, if the remaining values are the errors. So that's your FP and FN. Precision is the true positives divided by true positives plus false positives. So effectively, what you're calculating is how many of your correctly predicted values are true. So if you look at the true column for the predicted values, TP is your correct predictions and FP is your incorrect predictions. So if you just take the ratio, you'll get the precision. Now you have two terms here, true positive rate and false negative rate. So they are both related, and true positive rate is also called as sensitivity or recall. So true positive rate or TPR is your true positives divided by true positives plus false negatives. So if you look at the rows and the actual values, the true row, that's the category true, that is 1. And if you look at your predicted values, the correct predictions are TPs and the wrong predictions are the FNs, right? The false negatives. So your TP divided by TP plus FN will give you the ratio of actual true values which are correctly predicted. And equivalently, your false negative rate would be Fn divided by Tp plus Fn, right? So all the actual values that were supposed to be true uh, in terms of your predictions, the Fn are the wrong values. So you divide that by the total number of predictions for the truths, and you will get your FNR. So the net goal of the model will always be to have a higher TPR and a low FNR, which means more correctly predicted true values. And along with this, you have these two other error metrics. So it's the true negative rate and the false positive rate. So the true negative rate, which is also called as specificity, is your true negatives divided by the true negatives plus false positives. So let's go back here. What you will see is your true negatives are the correctly predicted Y values for the class or category false or 0, whereas the FPs, which are the false positives, are the incorrected predicted values of Y for the category false or 0. So again, you want to improve the ratio where TN is higher and FP is lower. And that's what these two error metrics are. So TN upon TN plus FP measures the actual false values that are correctly predicted, and the FPR or false positive rate, which is FP upon TN plus FP, it measures the actual false values that are incorrectly predicted, right? So we've shown you that. And false positive rate is also calculated as 1 minus specificity. You can try that on your own. Again, overall objective being you want higher TNR and lower FPR, which means more correctly predicted false values. So please be careful here. You're representing your class or categories, which is 1 or 0, as true and false. So you want more correct true predictions, more correct false predictions, and a lesser number of incorrect predictions for both. And that's what these ratios are. So you can combine all these different metrics and build a model which gives you a good result. Now let's look at the ROC curve or the receiver operating characteristic curve, which is used for evaluating binary classifiers. So up till now, we saw some numeric interpretations. This is a visual chart. What it does is it plots your true positive rate against the false positive rate. True positive rate being the correctly predicted actual true values, and false positive rate being the incorrectly predicted actual false values, right? So now it's kind of obvious that we want the TPR to be as high as possible, so close to 1, and the FPR close to 0. Remember, it's your TNR which would have been close to 1, but the FPR is close to 0. That's what we want. And if you see the plot here, you can see that if you draw different curves which represent your model's prediction accuracy, so as you get a better and better model, the accuracy improves, your false positive rates reduce, your true positive rates increase, and the steeper the curve, the more optimal the model will be. Now, there is something called as a decision threshold, which is used by the classifier to determine that split between the two classes, right? See, your one category is 1, the other category or class is 0, so the true and false. Now, what determines that some y predicted values go to the 0 class and some go to the 1 class? Remember, right? The input values could be continuous data with the real numbers, and your output also will be a combination of that. So it will be a real number, continuous values. So you have to find a way to split that into different groups. So you'll need a cutoff threshold or a decision threshold. We'll discuss that when we build the models. So for now, what you need to understand is that as this curve gets steeper and steeper, as you can see, you get smaller and smaller values for FPR and higher values for TPR. And that's what we want to do. And if you look at the topmost left corner of this chart, that's your optimal threshold. Now, that's the ideal scenario. You know, all your true values and false values are correctly predicted, but in the real world, that won't happen. You'll run into problems similar to what we saw in regression, which was the bias variance trade-off, the overfitting and underfitting of the model to the data, depending on its complexity. And similarly, what you have here is you use the concept of cost benefit analysis when selecting the optimal decision threshold. Look, so the exercise of building all these machine learning models is you want to build them as efficiently and as cheaply in terms of resource consumption as possible. So that always is a cost benefit analysis, and that's the concept which is used here. So this ROC curve, if you can see, now it's a plot between the x and the y axis. So if you can see in a simple classifier, only half your true and false values are correctly predicted. And as the curve gets steeper, you get more accuracy. And the area under this curve, if you interpret that, it means that the more the area under the curve, the steeper and more accurate the model and the curve are, and that effectively is your AUC curve, which is the area under the ROC curve. So it varies from 0 to 1 because as you can see, this is the area of the curve from here to here. And the larger this area, the better the classifier. So what it's basically doing is giving you a summary of the ROC curve. And what you must note is that it indicates the probability that the classifier ranks the true values higher than the false values. So one of the reasons for doing that is, see, if you're plotting the TPR and the FPR, right? And what you'll find quite often in the real world is when you're indicating something as true, it means it's a good result and you want more of that. And if something is false, you want less of that. While they are the output predictions of your model based on the data given, but most likely the true values are of a higher concentration in the data compared to the false values. So you want more of those results and less of the false results. So these are all the different error metrics that we feel are useful for classification models. If you want to see uh, all other different metrics that can be used, you can go to the scikit-learn site and look at all the different metrics, their definitions with examples, and you can try the different metrics as you need for your models. Okay, so now let's look at the sample data we'll be using for the classification model. So there are two sample data sets we are using. Both are from very good public data websites. One is data.world and the other is Kaggle. I'm sure you might have come across Kaggle, especially for its machine learning and other data science competitions. They are good data sources. Similarly, data.world. But be careful if you're using the data for commercial purposes. So just check the data policy that yeah, the data is public and it can be shared with everyone. Generally, it's stated. So we are using public data sets. The first data set we'll use is from data.world. Uh, it's NBA rookie statistics data. NBA rookies are people who haven't gone professional yet. So if you follow a little bit of basketball and American professional basketball, you'll find that all the players go through different stages, and there's a lot of statistics which is collected on them. And in this particular case, what we are trying to do is predict the 5 year career longevity of the NBA rookies. So, will they last in NBA for 5 years or more? And to assess that, you have a lot of information about each player. So, these are your X independent variables, and your Y dependent or the output variable, which is your class or category, is the career length being greater than 5 years or less. So you can see, some of these terms are self-explanatory. How many games are played, how many minutes you played in a game, how many field goals were attempted and made, how many 3 points were attempted and made, what were your offensive rebounds, what were your assists, steals, and so many other different useful statistics. And your target is your 5 year career length. So greater than or equal to 5 years or less than 5 years. So this is your data dictionary. We'll show you what the data looks like during the model building exercises. And just to show you the data source, so the data.world website and the particular data set. So it's the binary classification exercise data set. It's a public data set, so you can use it. So again, you've got the dictionary here, you've got a cut of the sample data, and you can download this data on your own too. And now let's look at the other data set. So this is from Kaggle. Again, it's a public data set. It's from the IBM Maratona application. It's a online educational platform called Tortuga Code. And what they've done is they've got this information regarding students related to their data science and web technologies, front end and back end skills. So, what it does is it uses all this information, which are your X independent variables, and you have things like what were the beginners and advanced courses they took in each category, uh, how many hours they studied for each category, like data science, web backend, web front end, and then what were their average scores in the tests for each category. And using this information, you're now trying to build a recommender system which predicts the categories for these students for these different skill sets. So whether you are a beginner or an advanced data scientist, web front-end engineer or a back-end engineer. And what we'll do is when we build the model, we'll show you what the data looks like. For now, this is just an introduction to the data set. And we'll also show you the Kaggle website where we took this data from. So, you can check out this particular exercise here. Again, it gives all the explanations, a cut of the data, and you can download it on your own directly from here. But we've also provided both of these data sets as part of our full package of data and code. So let's go back to the GitHub location again. It's the same place, data science course, machine learning data analytics. Within that, under the data folder, you'll find the Kaggle dataset and the data.world NBA rookie dataset. There is some extra data available for the Kaggle data, like for example, the to be scored. You can easily use that for validating and further testing the model. So we'll show you that. And for the Python code, again, under examples, if you go to the classification folder, you'll find all the Python code there and you can download and use it. Okay, you can always download the entire data science course material at one go. But with that, we'll end this introduction to the classification lecture series. So hopefully you've got a feel of what the basics are for classification, the error metrics, and the data we'll be using. And in the next lecture, we'll start discussing the different models that are built for classification. Thank you.